Okay, welcome everyone. Welcome to the second webinar on thermal energy management technologies. I'm Tony Roskilly, and I'm a Professor of Energy Systems at Durham University in the UK, and a Director of Durham Energy Institute. This webinar is part of a series of events and activities for a UKRI Innovate UK funded project, UK-India Foundation Industries Sustainable Thermal Energy Management Collaboration, which is led by myself, and we're working very closely with colleagues in India from Amrita University and the UK-India Business Council. This new partnership has been formed to help the foundation industries in India and the UK to decarbonize, and using the latest thermal energy innovation. Foundation industries such as metals, cement, paper, glass, bulk chemicals, for example, are pivotal to both the UK and India economies, and are energy intensive and release an enormous amount of waste heat and harmful emissions to the environment. It is therefore imperative that the foundation industries decarbonize, use materials and energy more efficiently and effectively, and reduce their contribution to greenhouse gas emissions if they are going to be able to sustainably grow and flourish. The UK-India FI-SusTEM collaboration aims to tackle the challenges of transforming the foundation industries by focusing on optimization, efficiency improvements, and energy cost reduction through the capture, storage, and utilization of waste heat through technology innovations to exploit low-grade heat for power, heat, and cooling applications. Our second webinar today will cover important topics relevant to the scope and focus of this collaboration. So our first speaker is Professor John Counsell. He is a part-time research professor at the University of Chester and leads the Digital Energy and Control Systems Research Group. He previously was the head of domestic energy research at the UK electricity industry, and held the BRE chair in energy utilization. He is also owner and managing director of the energy systems control and modeling company Advanced Control Partnerships, which he founded in 2013. This company has developed models and control algorithms used in practice globally by Fujitsu, Glen Dimplex, BRE, and many others. Professor Counsell was awarded the UK Electricity Industries Churchman Prize in 1997 for inventing SELECT, now considered to be one of the world's first implementations of demand-side response using energy storage. Advanced Controls current research and client work is focused on complex energy system modeling and control algorithm development using AI and nonlinear dynamic methods. So over to you, John, for your presentation.
Thank you very much, Tony. Welcome everybody this morning. It is this morning here anyway. Okay, thanks very much for the intro, Tony. I think you covered all my points very well, thanks. So that makes my introduction of Advanced Control Partnerships very simple, because I think you've already done it. So what I'd like to talk to you today is a little bit of talk to you about a journey in the area of energy system design, in particular the use of modeling to understand how best to design energy systems. And this started way back in around about 2007. Well, probably started in the 1990s, to be fair, but we were very primitive in our modelling approaches back in the 1990s compared to today. In 2007, as Professor Roskilly mentioned, I was chair for BRE, Building Research Establishment, and we set about trying to understand how to do dynamic system modeling to be able to deal with the complexity of an energy system, which grew in complexity every day with the introduction of renewables, demand-side response, energy storage, many other aspects of technology that we see emerging. And that was going to be very complicated in the buildings industry to start with. And that's where I started in 2007 and have moved forward more and more into more complex energy systems, particularly associated with heat recovery, combined heat and power systems, and also private wire networks and local energy systems. So that's what I'm going to do, is just tell you a bit about that journey and where we are today. And I'll start with some of the basic methodologies that we developed for the building industry and how we're using those approaches now in these more industrial complex systems. So the first thing I'm going to do is introduce multi-vector energy systems, what we mean by multi-vector energy systems. Look at some of the advanced control companies' capability, which is basically dynamic energy modeling, system modeling and R&D, and basically the tool developments. We've got software tools such as Power River, and then talk about the other aspect about the importance of control algorithms and how we use control algorithms, not so much to design controllers, although we have projects like that, where we are controlling and optimizing a complex energy system, but more to do with how we use control algorithms to make high-speed simulations. If anybody has had any experience with simulation of energy systems over 1 or more years, once you get quite a complex energy system model, the actual simulation itself can take quite a long time to run. And if you're taking, say, 20-30 minutes to run an annual simulation of a complex energy system's performance, then the ability for that modeling tool to impact your design is much reduced if you could do it in several seconds. Because the faster your simulation can be, the more and more likely you're going to be able to integrate simulation and optimization into your design process. So that's what we focused on very much in advanced control, is accuracy and speed of simulation. Then I'm going to go into the industrial side, having covered the history of our modeling, and talk about some opportunities in industry, particularly the free energy and carbon offsetting that we can do by heat recovery in industrial processes and what we might be able to do with. And I'm going to talk to you about a particular case study I've been doing with our local company, with the University of Chester, Urenco, which is a nuclear enrichment company, uranium enrichment company. And there I'll show you some of the ideas and concepts that we've been thinking, and I'll just leave you with sort of 4 key conclusions of my journey so far. So first of all, this is a slide I use very often, but we've got a changing energy landscape, and in the United Kingdom that's been changing quite dramatically since about 2006. And in 2006, the United Kingdom, you could argue, has reached peak electricity so far. That doesn't mean we won't be using a lot more electricity in the future, but we haven't actually met the 67 gigawatt peak of electricity demand in January of 2006. We haven't really met that, anywhere near it. Now here in 2021, we've just hit about 47 gigawatts. And in that time, the carbon intensity of our national grid has reduced from 0.57 kilograms per CO2 per kilowatt hour to 0.25. And actually our gas heating, particularly in industry, we tend to be lucky to achieve 80% efficiency in commercial buildings, and even less in industrial applications. So our actual carbon intensity from gas heating is actually currently more than our national grid for electricity. But this really, those figures tell, they tell a distorted message. And, we could assume that the reason for the decarbonisation of our grid in the UK is down to the injection of more renewables and biomass into our national grid. Renewables typically in the UK being wind power and photovoltaics. But it's a little bit distorted view that we've lost 20 gigawatts of demand off the national grid. And more than 70% of that carbon intensity saving has come from demand reduction, not from the injection of renewables. And those of you who may be familiar with primary energy calculations will probably be able to work that out. So it's not just about, in the UK, it's not just about the success of the electricity decarbonisation in the UK. It's as much about demand reduction as it is about the injection of renewables on the supply side. And this is creating a massive change of focus now, because if we're trying to reduce carbon dioxide further in the UK, there's probably a limit to how much we can reduce electricity demand with the emergence of electric vehicles. So we have a question mark, and we have to focus very much on heat. And heat is obviously a big factor in our homes and also in our offices, but in particularly, it's a big factor in our industries. And improving the energy efficiency of our industries is a very important thing. But I want you to leave you with this problem with why we need to talk about multi-vector. And the simple example of multi-vector I've got is the simple light bulb. And historically, on average in the UK, in the 2006 period, we all had incandescent or tungsten light bulbs, and they were using about 60 watts of electricity. And now today we have typically filament LED light bulbs, which are all using about 4 watts of electricity. So you can see where a lot of that electricity demand reduction has come from. 56 watts of light bulbs, and there's a lot of light bulbs in the UK. And every day goes by, a tungsten light bulb is replaced by an LED light bulb, and that is continuing, although it has slowed quite dramatically in the last 2 years. However, it's a little bit more complex than that. Everybody could say rejoice, and we've saved lots of carbon dioxide. But actually, the tungsten light bulb provided 59 plus watts of heat to the household. And as UK homes need heating, that's a very important contribution. Every light bulb is giving us 59 watts of heat. Now the LED light bulb has only given us 3 watts of heat. Most of that is in the power electronics, which if they were made more efficient, would probably be 1 watt of heat. So unfortunately, we've got 56 watts of heat shortfall to heat our homes. And it's not surprising that the United Kingdom's gas consumption has accelerated in demand. So actually, as we stand at the moment, the LED light bulb is not a carbon-saving device in the United Kingdom. It's doing very little, actually, because 0.25 kilograms saved on the national grid is almost been replaced by 0.25 kilograms of extra heating required. So I'll let you all sit and think about that one. But what's happening is if you just consider electricity in its silo and heating in its silo, then you make the wrong conclusions. You've got to look at the full system and stop being so siloed about your individual energy sector. So Advanced Control Limited, we go back to the days when I was sitting with BRE chair, and I founded the company because I was asked by a number of electricity appliance manufacturers, particularly electric heating companies in heat pumps, storage heating, underfloor electric heating, and all sorts of other novel electric heating systems we've seen over the years, to actually try to understand how to introduce new electric heating technologies into the building regulations of the United Kingdom. And it became very clear that we didn't have any tool that could actually look at the multi-vector aspect of heating and electricity in the home. So we had to model everything. And anybody who knows anything about heat pumps, the COP, or coefficient of performance of a heat pump, is not static. It changes dynamically with outside temperature and the return temperature of a radiator system, or if it's a warm air system, the air. So using simple sort of static calculations to work out efficiencies was just not good enough. And we had to move to producing a dynamic model suitable for building regulations. And I did that in partnership with BEMA, which used to stand for the British Electrical Appliance Manufacturers Association, but these days they just like to call themselves BEMA. One of the great things that we discovered was we started to learn how that we had to calibrate models with real data. The building research establishment had thousands and thousands of houses with real 1 minute stamped temperature and energy consumption data. So that gave us an opportunity to actually calibrate our dynamic models to actual real data. And this is what we've done over a significant number of sampled houses, is typically look at the monthly comfort temperature in the home versus the monthly energy consumption. And the red line is the real data, and the Power River results, which is the model, are the blue data. So we have an extremely good correlation. And the most important thing we learned from this dynamic simulation, getting these things, is that you have to work out what the key parameters are that you need to calibrate against. And in the UK homes, and all homes all over the world, you can't just calibrate against monthly energy consumption. You also have to make sure you've got the same temperatures. And I see so many academic papers where people are calibrating just against energy consumption, and they're not looking at key state variables to see if actually everything is the same. It's very easy to compare apples with oranges. You need to be comparing apples with apples. And this is the way to do it. So we learned how to calibrate models, and we now started to automate that a little bit more and use some of our control algorithm intelligence and artificial intelligence to be able to automate the process of calibration. So traditionally, just to give you some details, traditionally, static models would take monthly averages, for instance, for solar gain. Well, we can use dynamic data, and we can use dynamic irradiation data from the Met Office or from the weather file to be able to get a more truly dynamic response, typically the sort of Poissonné distribution curve versus just a block constant. It makes a huge difference to the simulation and the efficiency of the systems. Outside temperatures were typically used with monthly linear interpolations in some cases, but in reality, outside temperature is up and down with somewhat chaotic period, typically colder during the night than it is during the day, and we can take that into account. We are challenged with wind speed. There's not, surprisingly, even with all the wind energy around, there's not very good data for wind speeds in urban environments, because we don't put wind turbines in urban environments. So we're working on wind speed. So that's one thing of research at the moment. We need to get better wind speed models for our energy system modeling. In the company Advanced Control, our expertise is really in nonlinear systems and nonlinear complex dynamic systems. And we've perfected the art really back from our military origins of advanced weaponry, where all these algorithms were developed And I'm pleased to say that I took the plunge to use them a bit more wisely many moons ago. And we're using them in energy systems now. And basically, in a nutshell, the challenge is that when you're trying to model an energy system, you kind of know what your outputs are. For example, if you've got an industrial process, you might know that the temperature is 300 degrees and you need to get to 300 degrees. And you know broadly the dynamics of the process and its insulation and everything else. The problem is you need to work out what input energy you need to put in to be able to get where you want to be. And it's only then that you can do comparative studies. So this plant, this process, is highly nonlinear, mostly discontinuous, and got some very nonlinear thermodynamics, and also could possibly have some quite complex electrical circuitry too. And they're all connected together if you're going to start doing electric heating and other types of things like heat pumps. So you've got a very complex nonlinear dynamic system with discontinuities, and you want to really know what you need to put in it to get a certain output. That means you have to invert the plant or the dynamics, plant to the -1, if you like. So what are those algorithms? That's the big challenge. And that's where core competence of advanced control partnerships is. Now, one of the things we discovered fairly early on, around about 2012, we published a paper on this in the energy journal by Elsevier, was how to calibrate a model using inverse dynamics. And then we realized not only was it great for calibration, but we also noticed that we could actually reduce an annual simulation, dynamic simulation of, say, a 4-zone house from around about 10 to 15 minutes in most dynamic energy system modeling environments down to less than 60 seconds by using the control algorithms. So we got a turbo increase in speed of simulation, which allowed us to then integrate the simulation into design processes, which I'll talk about some more in a minute. So basically, the simulation is based on inverse dynamics, and basically we have to cancel the nonlinear dynamics of the system. We basically have to invert it, and we have to decouple all the control variables because there may be more than one output. There may be, for example, a desired set point of taking power from the national grid, and at the same time, a hot water heat network temperature, and at the same time, temperature of several zones in a building. And we have to meet them all at the same time. So there's multiple inputs and multiple outputs, and these all have to be decoupled. It's quite a clever piece of maths, if I may say so. So, for example, if we were trying to do a dwelling model, a house model, you want to know what the heat required is for a certain target temperature, then you basically tell the inverse dynamics what the target temperature is, and it will calculate dynamically, second by second, minute by minute, 5 minutes, half an hour, whichever time interval you want to use, it will work out what the heat required is in that dynamic interval. The speed of simulation was so impressive that we managed to integrate it into Glen Dimplex's design processes. Glen Dimplex is the largest electric heating manufacturer in the world, and the Power River model was used to design the control algorithms and the insulation levels, etc., in their new range of quantum storage heaters, which is now the de facto standard of storage heating in the United Kingdom, Canada, and now on sale in Japan. So moving on from the domestic environment in the journey, we very quickly established that this wasn't just about domestic and commercial buildings. We needed to expand to an all-integrated tool whereby we could look at all types of energy systems, be buildings, industry, and use the multi-vector aspects to be able to integrate them all together in an all-in-one tool we call Power River. And this allows us, and I know that Durham University Professor Roskilly's group are using these terms, sort of digital energy twin. This tool allows us to get close to doing a kind of virtual dynamic representation of a fully integrated energy system, which you could look upon as being like a digital energy twin. And the energy twins of the buildings are integrated within it. And that could be hundreds of buildings. The benefit of this approach is that we can look at the impact of future technologies, look at performance gaps between the real system and the actual simulated idealistic system. It's a holistic approach, so we can be open and not too concerned about introducing new metrics at any time. It can be integrated into the design process because it's fast and quick to simulate. And actually, the dynamic simulation tools can be simple and complex, whichever you want. And the strong foundation is that it's born out of strong, highly peer-reviewed research in the building research establishment days. Kawasaki City was one of Advanced Control's clients, and they wanted to integrate their local regional PV into a private wire network to heat their main commercial, to heat and power their commercial office with the sunshine. So we modeled this building, and this is an example of the dynamic output over the year, the green being the outside temperature and the red being the zone temperature. And up here, by the way, this is starting in the middle of the summer. It's not, starting in the middle of the summer because the temperature is very high, not starting in January. And then the blue line is basically the required temperatures. And what we did was we set the heating temperature to 21 and the cooling temperature to 25. So that's why you can see the red line is higher in the summer and lower in the winter, because there's don't really need cooling much between 21 and 25 degrees. So that shows you how you can do the very, very sophisticated approach. What was interesting is that we also did a similar used a bit of AI and optimization to look at calibration, and those are the total electricity, real and predicted. The top one is the metered, and the green is the predicted. So by the way, we got that graph almost the first time, not without too much calibration, which was quite remarkable. So that allowed us to baseline the model so that you could try all sorts of technology. And one of the technologies we wanted to use was to actually use an electric heat pump. So that's what we looked at in the project. Originally, it was a gas-fired heat pump, could you believe? And we found that one of our challenges that I leave you with is that actually gas metering is very, very poor. There's not many gas consumption meters in premises, and it's very difficult to actually calibrate against measured gas metering. We found it very hard, whereas electric metering was very easy. And I think that will be the case in industry as well. So coming to the industry, we have moved on in partnership with Urenco and the University of Chester. We set up a project to look at using Power River in a Urenco plant, an enrichment plant, which uses an enormous amount of energy, where it's actually spinning centrifuges, cascades they're called, where they spin uranium, which has been sublimed into a gas, and we spin it really, really quickly. There's lots of friction, lots of heat generated, and that heat has to be taken out by cooling towers in the blue graph. So another source of energy is the enormous amount of electricity to drive all the electric motors. I think there's about 25 football pitches of these cascades, if you know the size of a football pitch. 25 football pitches of cascades, thousands of electric motors needing gigawatts of power, huge substation to power the plant. And there's an enormous amount of heat in the substation. So we work with a company called M&I Materials, using a new synthetic cooling to actually take the heat out of the substations. And also there was massive amounts of steam losses in what's called a gas kiosk, and there's an opportunity for heat recovery from steam losses. Again, we looked at all those heat recoveries. So in summary, there was about 14,000 tons of CO2 to be offset from free heat if we could recover it, which was enormous. At 19 1-megawatt turbines, and typically costing about £45 million. We could recover the heat equivalent to heating about 1,500 homes. And this was just one industry. What if we did that for quite a lot of these types of industries? It would have a huge impact on our future carbon emissions from heat that we can't really easily do. So all these cooling towers, if you have a look at this, this is the roof of the building to the left. You can see all these cooling towers spread across this plant, which is equivalent to these huge numbers of football pitches. So what we wanted to do was to replace that cooling tower, and instead of wasting that heat out to the atmosphere, which probably explains the why where I live on the world in the UK is a good couple of degrees warmer than Manchester, which is about 40 miles away. And I know where our heating is coming from. We won't be having that much waste heat going into the atmosphere. And we could actually recover that heat and put it into a heat network. So typically, what we're looking at is a very complex energy system concept, which is still connected to the national grid through that substation. But we're going to put in parallel to the private wire network, which was powering all the enrichment processes and buildings. We would put in a low grade, and sorry, it's a little bit hard to see, it's in an amber color here, a low grade heat network. And that would recover heat from the transformer, and it would also recover heat from the steam. And also, we would have a combined heat and power plant here, which could be using gas or and now this is very much relevant to Professor Roskilly's area, bringing in hydrogen into the trigen and so combined heat and power and trigen environment to produce heat and recover that heat into the heat network. We also have been looking at this as being over the fence type heating, because we have large local authority housing estate close to the enrichment plant. We could drive that heat network to the housing in Ellesmere Port, the local town. One of the things we have noticed is that low grade heat is not the greatest necessarily for heating anything, never mind industrial processes, but also buildings. So we sort of are looking now to deploy heat pumps in series and in parallel with these heat networks to supplement the buildings when the heat demand is very, very high. And finally, obviously, working with a nuclear company and an enrichment company. Oh, sorry, I did forget one other very exciting thing is in the UK, over the fence heating can also now explore, the use of horticulture and farming. There's a little link there in the presentation to low carbon farming website, where the UK is using heat recovery to actually grow exotic fruits and kind of things that would normally have to be transported to us from all over the world. We can now grow them in the UK by using industrial heat recovery. And to come to my last point, nuclear, you'd have to have a nuclear power plant in there for your concept somewhere if you're working with the nuclear industry. And small scale micro nuclear plants are now being researched, and Urenco's concept is called the U battery, which ultimately could replace the gas and hydrogen CHP plants. So finally, just very quick slides. Power River Tool, it's an engine that can hook into Excel or Matlab. That's a typical front end that we developed in Excel for M&I materials. The important thing is that when we start to do these kind of digital energy twins, it's a fantastic thing to work with the industry with real data and use some of our automated tools to calibrate the models, and it really helps them in their design process to optimize their design. And then in Matlab, we've integrated the tool and embedded it in Matlab, and we can output results to Matlab itself, which Matlab, if you know it, is fantastic with data. And we can also output in text files and CSV files that we can pull into virtually anything, into a web page or into Excel or something like that. So in conclusion, now the world of complexity is such, we've got solutions to decarbonize electricity, and we've got solutions to reduce the demand from electricity. So we've got a huge challenge of how to work out how to make sustainable heat. Industry is a big contributor to that. Multi-vector and local energy system design is a key issue, and we need tools to help with it. So dynamic modeling tools to create debts will help us to optimize size, work out what the best technologies to use in our particular case are. And then finally, from an advanced controls perspective, we pride ourselves in our intelligent control algorithm development technology has found a home in being able to bring super high speed modeling and accurate modeling of local energy systems of any complexity. And we'd be delighted to help anybody who wants this kind of thing.
Okay, thanks very much, John, for a very interesting presentation.